Good day, you talk. This is a short video on a couple of examples of torque being applied to moments and situations of equilibrium. So I've taken a couple of examples out of your SciPad and a couple of recent NCA examples. I'll just whip through some of the calculations and the way of thinking through some of these problems. Hopefully it'll give you a bit of a help with answering yours when you go through them. So for this first one, this is at the SciPad. A family is playing on a seesaw as shown below. You've got the father on the left-hand side and the mother and the daughter on the right-hand side. First part of the question asks you to label the diagram with the torques as either clockwise or anti-clockwise torques. So an anti-clockwise torque will be a force that tries to turn the system in an anti-clockwise direction around the pivot. So in this instance, the anti-clockwise torque is caused by the father, because if you were to get rid of the mother and the daughter, the seesaw would turn anti-clockwise or around to the left. So those are your anti-clockwise moments. Sorry about the drawing. And on the right-hand side, both the mother and the daughter, if we were just to have a look at the way their force is applied around the pivot, they are causing a clockwise torque because they are trying to turn the seesaw in a clockwise direction. Okay, part B asks you to work out the weight of the father. You'll notice that the seesaw is currently balanced, it's in equilibrium, it's horizontal, and the torques caused by the mother and the daughter are equal to the torque caused by the father. So the first statement we make is that the clockwise torque equals the anti-clockwise torque, and after that we need to apply the torque formula to each of the people on the seesaw so that we can work out what the force of the father actually is. So we'll start with the clockwise torques. We'll begin with the mother. So we want the force of the mother. She is 60 kilos in mass. Multiply that by 9.8, the acceleration due to gravity, and multiply that by her distance to the pivot, which is 0.8 meters. We're going to add to that the torque caused by the daughter because she is also creating a clockwise torque. It's slightly easier here because we don't have a mass, we actually have her weight, so 343 newtons multiplied by the 2 meters that she is from the pivot. So those are the clockwise torques, and they have to equal the anti-clockwise torques. Now, we don't know the force of the father, so we'll just call that Fw, and he is currently sitting 1.5 meters away from the pivot. The next step for this is to calculate what each of those values is in the bracket, and then you should see the only unknown in that equation is Fw. As we carry on working through this equation, we have 60 times 9.8 times 0.8 and 343 times 2 is equal to Fw times 1.5. So that becomes 470.4 for the mother, add 686 for the daughter, that is equal to Fw times 1.5. That gives us 1156.4 equals Fw times 1.5. So then we divide both sides by 1.5 to find Fw, and you should end up with Fw, or the weight force of the father, as 770 newtons. This is another example out of your SciPad that caused a lot of problems when it was set as an NCA paper. The reason for the difficulty here is a case of identifying the pivot. In this particular example, it does tell you that the thumb is the pivot, so that is the point around which you need to work out your torques. If you have a look at the diagram, you'll notice you've got a finger underneath providing an upward force, while the plate itself provides a downward force. So that's how you end up with your two torques. One clockwise, caused by the plate wanting to cause the system to drop that way. Meanwhile, at the other end, you have a thumb that is pushing down. You've got fingers rather pushing upwards, trying to basically turn the plate that way around. Now, if you have a look at those two arrows, this one is going clockwise and this one is going anti-clockwise. So the trick with these questions is to realize that the thumb at the edge of the plate is the pivot, and you've got a torque caused in the anti-clockwise direction by the fingers multiplied by 0.1 meters, and a torque created by the plate creating a clockwise torque, which is 7.84 newtons multiplied by 0.25 meters. Below, I'm going to show you a worked example of this with a cup on a plate. So in this particular example, we've got a waiter carrying a tray with a cup on it. The tray is 40 centimeters wide, and the cup is placed at the center of the tray. The mass of the cup is 360 grams, the mass of the tray is 640 grams, and the thumb of the waiter is placed 8 centimeters away from the fingers underneath. First question just asks you to work out the force of the tray and the cup. That's a fairly straightforward equation. Weight is equal to mass times acceleration due to gravity, which is 9.8. So if we add the two masses of the cup and the tray up, multiply that by 9.8, then we end up with a force of 9.8 newtons. Part C and D, you're after labelling certain features of the diagram. So we're after labelling the diagram with the information from the question for part B. So the overall width of the tray is 40 centimeters or 0.4 meters. The distance from the thumb to the finger is 8 centimeters or 0.08 meters, which is there. Then we've got the weight or the force of the cup downward, which is that arrow there, and then the weight of the tray downward, which is that one there. The tray arrow is longer than the cup one because it's a greater mass. Part C, you're asked to draw the clockwise and anti-clockwise torques acting on the tray. So, acting on the tray. The clockwise torque is created by the finger and works upward in this direction. It's just drawn with a straight arrow, not a curved one, as I had done in the previous examples. And the torque of the tray and the cup are created from the center of the tray, straight down like that. So there are your clockwise torques, trying to turn the tray and the cup round to the right, and your anti-clockwise torque is created by the finger pushing upward there, remembering that the thumb is the pivot. Last part of this question asks us to work out the upward force provided by the waiter's fingers on the tray. You'll notice I've still started off the answer in the same way, stating that the clockwise torques are equal to the anti-clockwise torques. In this particular example, it's the thumb that is the pivot in the system. A lot of students made mistakes because they chose the fingers as the pivot and not the thumb. It's an easy mistake to make. Just remember, in these particular contexts, if you find one like this, it's the thumb that is the pivot. It does quite often say in the question, but this one's been a little bit more mischievous or mysterious, I suppose. So now that we've got our clockwise torques equaling our anti-clockwise torques, we just fill it in the same way as we did before. We want the force of the tray and the cup multiplied by the distance of the pivot. That's going to equal the force provided by the fingers multiplied by the distance that the fingers are from the pivot. So the tray and the cup, they are equal to 9.8 newtons, and they are 0.2 meters from the fingers, and from the thumb, and the fingers, we don't know the force of those. They're multiplied by the 0.08 meters that they are from the thumb. So filling that out, the force of the fingers is equal to 9.8 times 0.2. You divide that by the 0.8 so that you get F fingers on its own, and that gives us an upwards force of 25 newtons. And that is that question complete. This question is from an NCEA paper a few years ago. It's just like the one that I put in the first video to you. We have some books sitting on a table supported by two legs or two upward support forces A and B. Table legs are 1.5 meters apart, and the books are placed 0.45 meters away from pivot B, support force B rather. Now both the weight force of the table and the books act vertically down. The support forces A and B act vertically upwards. The weight of the table, as I mentioned in the other video, is said to act from its center because it's a uniform table. Half of the table slab is supported by support force A, half of it's supported by support force B. So when we're treating it in a calculation, we divide its total distance by 2, and and that's how we work out where the force acts to create the torque. So we've got a 37 kilogram table, 7.4 kilograms of books. It is in equilibrium because the table's not turning or moving anywhere, so the upward forces equal the downward forces, but in this particular case we're going to have to work out the translational forces, in other words the torques. So we are after finding the support force provided by A, and if you remember the other day, if we're looking at finding support force A, we must treat B as the pivot and work out our torques to that mark. So what that looks like is the force at A multiplied by the distance between A and B is equal to the force of the table multiplied by the distance to B, and added to the force of the books multiplied by the distance to B. So that gives us the force at A multiplied by the distance to the torque created around pivot A is equal to the torque created by the table plus the torque created by the book. When we fill in the numbers, we have FA times 1.5, because that's the distance from support force A to support force B, multiplied by 37 times 9.8 to get the force of the table, multiplied by half its distance, which is 0.75 meters. Add that to the 7.4 kilos times 9.8 for the weight of the books, and multiply that by the 0.45 meters that they are away from pivot B. Gives us FA times 1.5 as 271.95. Add 32.6, and then to work out FA, you add those two numbers on the right up and divide by 1.5 to end up with 203, or approximately 200 newtons acting vertically upwards. That is a fairly common style of question that you're likely to find in your NCEA paper. If you end up getting one like that, by all accounts, consider yourself kind of lucky. I'm going to finish this video off with probably one of the harder moments questions that I've seen in papers in the past. The reason it's bizarre, well, you'll see in a moment. It's technically, it is a balanced system, but it's not horizontal, and because one of the weight components acts at the point of interest, people got all sorts of confused.